Hi everyone, today we are going to cover lesson 3.5, distance from a point to a line. And you might notice in your packages there was a typo. I think it might be called 3.6, but it is in fact 3.5. After this lesson, you should be able to determine the exact distance from a point to a line, as the title of the lesson suggests. So what exactly does that mean? Well, if I have a line somewhere on a grid, let's call it L1, and I have a point P, what is actually implied in this question is that I'm not just finding any distance from a point to the line, I'm finding the shortest distance. So that would be the distance from P perpendicular to the line L1. So in essence, what I need to do is find this point Q, that is the point closest to P on the line L1, and then I would find this distance using the length of a line segment formula. So when I say the exact distance, what is implied here is that it's the shortest distance, but I don't have to tell you that. Okay, so you need to know when I ask you for the distance from a point to a line that it is in fact the shortest distance, and the shortest distance means perpendicular. So let's do this in the form of an example, or let's learn this in the form of an example. So what I'm going to do is, we know this is not the answer. The graph is not the answer, we said, in analytic geometry, but we can still plot it to help us visualize what we're doing. So what I want to do is find the distance from this point D to the line 3x plus 5y minus 4 equals 0. If I want to plot this line, I have to put it in y equals mx plus b form. And what we'll notice is that the line actually isn't very nice to graph because the y-intercept is obviously 0 4/5. But remember, we're only doing this for a visualization, so the graph actually doesn't matter. What I'm going to do though is I'm going to plot at 4/5, which is 0.8, and then I'm going to go down 3 units and across 5. So I'm going to go down 1, 2, 3, 1, 2, 3, 4, 5. Okay, 1, 2, 3, 1, 2, 3, 4, 5. And I think that's enough. If you grab a ruler, it's enough for us to get the visual of what we're doing. Doesn't have to be perfect. Now, we'll call this L1. So in essence, what I need to do is find the distance, this pink distance here, and it has to be perpendicular because we said what's implied is that it's the shortest line. It has to be perpendicular to L1. The way I do that is I actually have to determine the equation of the whole entire pink line. And then what I'll do is find the POI of the pink line and the line L1. We're going to call the pink line L2. How do I find L2? I'm going to use y minus y line equals m x minus x line. And as usual, we're going to need a point on this line, and we're going to need the slope of this line. I already know one point on the pink line L2, and that line is D. But I don't quite know the slope. However, I can find the slope because the slope of L2 is perpendicular to the slope of L1. And since I know the slope of L1, which we can call M1, is -3/5, it follows that the slope of line 2, which is m/2, is 5/3. So I've got 5/3 for my slope I've got 6, 4 for my point, and I'm just going to simply sub this in to the formula. I get 5/3 x, and if I multiply 5/3 by -6, I'm going to get -10. You can pause the video and figure that out if you need to. Y equals 5/3x minus 6. So what I can do at this point is I can look at L1 and L2, and if I go back to my picture, the next step is to find the POI of L1 and L2, and we're going to call it Q. Call the point Q. So I'm actually going to put this in a form that's a bit nicer for me to find the POI of. Okay, by the way, how do we find the POI? We use systems of equations, which we learned last unit, and we can use elimination or substitution to solve. So what I'm going to do is with L1, I'm going to multiply all my terms by 5. And then I'm going to bring the x term over. Why am I doing that? Well, it looks more familiar to us from our previous unit. When we use substitution and elimination, we normally did it in this form. I'm going to do the same thing here. I'm going to multiply all my terms by 3. And then I'm going to bring, I'm going to isolate, or I'm going to bring x and y to the other side. Again, if you want, you can pause the video and convince yourself that these two are the same. You can trust me on that. Okay, and now what I would like to do is use elimination. So what I'm going to do is multiply equation 1. I'm going to multiply equation 1 by 5, and I'm going to multiply equation 2 by -3, and I'm going to get 15x plus 25y equals 20. -15x plus 9y equals, what's this? 18 times 3 is 24, 54. So we've got -54. Okay, so my x's cancel out. I get 34y. And we get y is -1. Y is -1. And if I back substitute y equals -1 into equation 1, I get 3x minus 5 equals 4. 3x equals 9. Therefore, x equals 3. Okay, let's take a step back and realize what we've done here. So I want to call this point Q. And basically, what I've done is I've calculated the intersection point of intersection of L1 and L2. Okay, and if I look at this, actually it does look very close to 3, -1. Now remember, the question being asked here is what is the distance? So I actually need to figure out the distance from D to Q. So my very last step, which I'm going to do here in black, my very last step is to compute the distance DQ using length of a line segment. Okay, so I know that D is, well, Q is -3, 1, D is 6, 4, so I just substitute it into my formula. So I get 6 minus -3, which is 6 plus 3, 4 subtract 1 squared. DQ is 9 squared, which is 81, plus 3 squared, which is 9. DQ is root 90. Now the last thing I need to do is to see if I can simplify this at all. And I'm pretty sure I can. I can write it as 9, which is the largest perfect square that divides 90, and 10. So my exact shortest distance from D to Q, or the distance from the point to the line, is 3 root 10. Okay, let's do one more example together, and this time let's not use a graph. Okay, so this one actually involves an extra step, and let's change this from E1 negative 3 to E1 negative 5. It makes the numbers a bit nicer. So what we still have to think about is this point P, this line L1, and then we have to think about the line from P perpendicular to L1 that we have to find. And we know that L1 will have a right angle here. We're going to call this L2. Sorry, L2 will have a right angle there. Then we have to find this point we call Q. And then at the end of the day, we want to find the distance PQ. Now here we have an extra step because we need to find the equation of L1. And we're going to do that using y minus y line equals mx minus x line. Again, I need a point and a slope. Okay, so this is for L1. For L1, I have already 2 points on the line, negative 5, 2, or 3, 4. So I can use f or g, but the slope I don't know. So I'm going to find the slope of L1 using the slope formula. So this is the slope of fg. 2 minus 4 over negative 5 subtract 3 equals negative 2 over negative 8, or 1/4. Okay, so I know my slope here is 1/4. So I'm going to use, let's use g because both numbers are positive. So I have y minus 4 equals 1 over 4. X minus 3, I'm going to have fractions here, but that's okay. I get 1/4 x minus 3 over 4 plus 4. Now I have to combine these, and the way I do that is by finding a common denominator. So I'm going to write the 4 as 16 over 4. Okay, here we go. Plus 13 over 4. Now, if you remember from the last example, this is L1, but we're going to write it in a better way so that we can solve a system of equations later. So I'm going to multiply both sides by 4, and then I'm going to move the x term over. And I'm going to call this L1. Alrighty. So for L2, remember that what we need, again, we're going to do y minus y line equals mx minus x line. And for L2, the only point we know is P. Okay, so P actually in this case is 1, negative 5. I called it E. The point P is going to be, maybe I can write it like this, just to make it less confusing. We're going to call this E, and we're going to change this guy here to E. So in the end, we want EQ. So the point I know on this line is E, 1, negative 5, and the slope has to be perpendicular to the slope of L1, which I've already found. So I can just go here like this, and I know my slope is going to be negative 4. All right, let's sub it in. So we've got y plus 5 equals negative 4, x minus 1, y equals negative 4x plus 4 minus 5, y equals negative 4x minus 1. So this is L2, and we're going to rewrite it as 4x plus y equals -1. Now that I have the equations of both of these lines, I can solve for my point of intersection and call that Q. Let's do it. So my point of intersection will be -x plus 4y equals 13. 4x plus y equals -1. I could use substitution here. Why not? Let's use substitution just to practice it. Okay, so what I'm going to do is isolate y in equation 2. Y becomes -4x minus 1. Actually, that's what we had up here, so I know it's right. Then I'm going to substitute this into 1. -x plus 4x minus 1 equals 13. -x minus 16x minus 4 equals 13. I get -17x equals 17, and x equals -1. So if I sub this into equation 1, I know that -1 is 1, plus 4y equals 13, and then I'm going to get that y equals 3. Okay, so Q in this case is -1, 3. If I went a little fast for you there, you can pause the video and figure out how I got y equals 3. So my final step is to find the distance from E to Q. Okay, and we said that E is 1, -5, and we just found that Q is -1, 3. Let's find the distance between these 2 points. So I have 1 subtract -1, which gives me 1 plus 1 squared, plus -5 minus 3 squared. And this becomes 4. 2 squared is 4, minus 8 squared is 64. I get the square root of 68. Now I should see if this can be reduced further. Let's have a look at the factor tree. Okay, 68 divided by 2 is 34. Neither of those are perfect squares. (68) divided by 4 is 17. So I think that's the one. 4 is a perfect square, so I know it'll simplify nicely. So EQ in the end is 2 root 17. That is the shortest distance from the point E to the line given. All right.